It's a big, exciting Materion world. From the cell phones in your hand to the satellites orbiting the Earth, we are all around you. Come inside Materion to meet the people and hear the stories about how we bring it all to life every single day. Join us as we talk to our subject matter experts about topics and trends that are truly changing the world.
Okay, for the last 30 years, scientists and space nerds alike have been wowed by the beautiful and mysterious images that the Hubble Telescope has been beaming back to Earth from its vantage point 340 miles above. But in approximately 100 days, NASA will launch Hubble's successor, the James Webb Space Telescope, where it will orbit 1 million miles from Earth and attempt to show scientists the dawn of the universe. Hi, everyone. I'm Marissa Milliron, and I'll be your host for today's podcast, Minds Over Materials. And I'm joined today by two Materion team members who have been deeply involved with providing NASA some of the advanced materials from Materion that are part of this telescope and this technological leap into space. Welcome, Keith Smith and Martyn Acreman from the Performance Alloys and Composites business. Welcome, everyone. So to get started, Martyn, how did your involvement start with the James Webb Space Telescope?
Okay, Marissa. So in the interest of full disclosure, I was working for a fabricator when James Webb was really coming to life. And I was involved with Materion, working together as a very close team, trying to get our material selected for the James Webb Space Telescope, and but involved in much of the fabrication and the machining. So that'll be my perspective for the discussion. How did we get involved? Keith may be going to talk about this, but there was actually a competition. So there was a program called AMSD, Advanced Mirror System Demonstrator, that NASA placed two orders, one for ultra-low expansion glass and one for beryllium. And we all worked together really, really hard, developed, basically a new material, convinced, the team that beryllium was the right choice, and beryllium won. So that was a great time to be part of the beryllium industry, to be honest.
Yeah, especially to be involved with such an exciting project. So you got to work with Keith from the Materion side. Yeah. So Keith, what was the initial start of this whole program, and what was Materion's plans to get involved with the James Webb Telescope?
Well, Marissa, I think we can go back probably before you entered school. James, Materion's been involved with supplying beryllium for optics since perhaps the 1960s. In 1996, that's 25 years ago, the James Webb Space Telescope program was initiated. And initially, Martyn mentioned there were a series of programs and test programs to develop materials. There were probably four key areas of materials are being considered. ULE, which is a glass, beryllium. They also looked at aluminum, perhaps magnesium. So these development programs, there's a first one called Subscale Beryllium Mirror Development Program, SBMD, in which we actually developed 030 as a special grade of beryllium that would be an optimum material for a space telescope. So there was a new grade of material developed under this program. And then what followed was the AMSD program. And the goal there was to develop that at scale, could a beryllium mirror be made and polished and processed at 1.3 meter? It's a hexagon shaped mirror at full scale. The reason for that was to demonstrate beryllium would work as compared to other materials, and to develop the capability to make a large beryllium optic. Prior to that, the largest optic was about 0.85 meters in diameter, which was the Spitzer Space Telescope. So the good news is the program AMSD program was very successful, working with now General Dynamics, where Martyn was, and we won the competition. And in 2003, beryllium was selected as the material for James Webb 18 years ago. These programs take a long time. After that, we entered a contract and over about a 3-year period supplied all of the mirror blanks. What's interesting to note is at the time, the expectation was that the beryllium optics would be the longest lead time items in the entire program. The reality is everything for the beryllium optics went very well. The final optics were delivered in 2013 to NASA, which is 8 years ago. So we beat the program. And in fact, from a Materion and for General Dynamics standpoint, is we were on budget, on time, on schedule, which is outstanding. We really talked about that internally and celebrated the fact that we delivered the projects on time.
Wow, that's amazing. I feel like every time you have a project, there's always a bump in the road. So it's good to hear that everything went successfully. Was this the first time that beryllium had been used in space?
No, beryllium's been used in space for a long time. There were the weather satellites, the GOES program. There were other satellites with optical systems for NASA, and there continue to be. So this was not the first time, but these are certainly this will be the largest telescope launched into space by anyone.
And it all has beryllium in it. How exciting.
Yeah.
So what is unique about the beryllium mirrors in terms of the materials that have been used for other telescopes, such as the Hubble? What makes this telescope different from them?
Well, the first thing is the Hubble was a glass mirror. And whereas Webb will be a series of beryllium optics. What's important? Why did they select beryllium? The key criteria for a space telescope, and for Webb in particular, was it needed to be lightweight, be able to withstand launch loads. And these are vibroacoustic loads that shake the heck out of the whole optical system. The mirror will have to operate at extremely cold conditions, minus 400 degrees Fahrenheit. For engineers, that's about 30 Kelvin. And keep in mind, as compared to the Hubble, which was closer to Earth, which ran at a much warmer temperature. Not only this, but you need to operate extremely cold, but without distortion. So as the temperature cools down, optics and components tend to change shape, and the beryllium can operate at that temperature with very little, if any, distortion. The other reasons you want to select a material that's great infrared reflectance, and polished beryllium has an outstanding reflectance in the infrared range, and it can be fabricated readily at room temperature here on Earth and can be operated at cryogenic temperatures and still operate successfully. So beryllium, we're very low density, we're lighter than aluminum. It's 5 to 6 times as stiff as the alternate materials being considered. We've got great thermal conductivity, so you can distribute the heat very uniformly, very quickly. Great infrared reflectance, and it effectively won't distort at extreme cold temperatures. That's how you win the program.
Yeah, that sounds like a lot of really good properties that are going to make it successful. That's great to hear. So when the mirrors left the Materion facility, were they ready to use? Were they ready to go up into space?
No, Marissa. There was obviously, first of all, the last mirror blank shipped from Materion, I don't know, more than 15 years ago. So there's a lot of work being taking place on fabricating the mirrors, polishing the mirrors, testing the mirrors, coating the mirrors, integrating the mirrors into this, and then more testing and more testing. Clearly, with a spacecraft that is so far away from Earth, there's no opportunity to go and repair anything. Everything has to work. So, I was involved in, at the time, fabricating those beryllium mirrors. And I always remember talking to the program manager and saying, what keeps you up at night? And Jeff Calvert told me, he said, well, Materion's not really made this material before. And they've not made it in this size before. And they're going to split each billet into 2, and I'm not sure they routinely do that. And they have to deliver on schedule, so it fits in with the 9 machines that we're running, and we've got it all planned on a program basis. And he said that's really concerning. And I said, well, how did it work out? And the truth is, he said, absolutely flawless. the material was delivered on schedule, at the right quality, with the right paperwork, the right packaging. I think what was most encouraging to us at the fabricator at the time was the relationship with Materion. When we picked up the phone or sent an email, people were very responsive. They were excited about the program. It was just a really good time to be working on that program in the beryllium industry. So we got the segments from Materion. We had to machine them, and I think I told you earlier, so a segment would come in weighing roughly about 550 pounds, and it left our facility at 45 pounds. So
wow.
more than 90% of the material was recycled. The finished shipped part was a very small percent of the material we had taken from Materion. But the 030 was a huge success, not for just the reasons that Keith said, because it was very good at cryo at the the minus 400 degrees F. It was very stable. It had all of the properties that you'd want from beryllium that we sell. The high stiffness, low density, good CTE, and good thermal conductivity. But in addition, it really helped when we were trying to manufacture these very large parts, for a couple of reasons. One, it machined very freely. It had very low oxide content, so tool wear was very low. That was important because we could keep the tool sharper on these very long, large cuts. You imagine finishing these large mirror surfaces. You didn't want to change the tool halfway through machining a mirror surface, so that property of the material being less abrasive really worked well in this instance, and the stability of the material was also a big factor, and the fact that because we kept the tool sharper, we had less subsurface damage, less residual stress, and the material stress relieved very well. So all in all, we felt at the time that Materion did a fantastic job of supplying that material in that grade, the right material for the right application at the right time. It was, and I said already, that only, the finished mirror was 45 pounds out of a 550 pound billet. That was almost the lowest areal density of any beryllium mirror made, but actually AMSD, the Pathfinder, was even lighter. That was shipped out at 27 pounds, but we had to add weight back because it was so thin that the actual light weighting on the back of the mirror could be seen when they looked at it optically through the sheet thickness on the front of the mirror. So we really pushed the envelope of what was possible, and then stepped back a few steps to make it something that we could provide James Webb.
When you look at the pictures of the James Webb before it's going up into space, you see that it has a nice shiny reflective coating on that. What coating was that, and was that done after all the finishing machining was finished? Yeah,
so there was an additional step after machining. The parts were shipped to a company in California called Tinsley that is now Coherent. And they were probably the only company in the world capable of polishing bare beryllium optics of that size and that curvature. And they polished the mirrors and took them, another couple of years to do that. But using their proprietary technology, they were able to polish the mirror to an incredible finish. And then those mirrors were shipped to a coater, what we call a coater, to put the optical coating on, which was gold in this case. It was a protected gold. And that was done by a company called Quantum. And of course, while all of this was going on, Ball Aerospace was responsible for the engineering. They were responsible for the overall program management. They were doing assembly work. So these mirrors, I mean, there's a great NASA website where you can go and watch where the mirrors went on their journey, and they basically visited, I think, 11 different states, some more than others too. So really an incredible journey, or the start to an incredible journey.
That's super exciting. So what other beryllium components from Materion are included on the James Webb Telescope? Is it just the mirrors, or is there any of the additional structure made out of beryllium?
You got this one, Keith?
Sure. So Marissa, there are, first off, the mirrors. The Webb telescope has 18 beryllium, large beryllium hexagonal mirrors that fit in an array. And why are there 18 mirrors? Because if you just had one large 6.5-meter diameter mirror, you couldn't launch it. So this telescope actually has to fold up to be launched, and then it'll open up in space. So you have 18 what we call primary mirrors. Then there's a secondary mirror, a tertiary mirror, a fine steering mirror that were all beryllium. In addition to that, there were a series of components to hold each mirror in place. Each mirror has to be mounted on the back side of the mirror. There's these tiny little actuators that are mounted between the beryllium. You've got an actuator, and then you have what we call a hex pod, which is a hexagonal sort of shaped device to hold that mirror. And there's other little components we call wiffles and struts that are beryllium. And the whole concept there is each mirror has to be mounted to a structure, and each mirror has the capability that they can slightly adjust the mirror by pushing it. And you can actually flex the mirror just slightly to push it into focus. So I believe the alignment within, I saw a quote, within 1/10,000th of a diameter of human hair. So that level of precision. In addition, the telescope has a whole series of instruments underneath it where you're sending the beam of light to the instruments. And one was called NIRCam, which is an optical system, near infrared camera device, and their components including a large optical base made out of I-220 grade of beryllium. Martin, do you have anything to comment on those?
Yeah, so yeah, thanks for the lead in, Keith. So as you say, you know, this huge telescope is collecting all of this infrared light, and it's focusing it into an area where there are 4 instruments. And the one we're talking about right now, Keith, is talking about the NIRCam, is a near infrared camera. All of these instruments have to work at, or they work much better at cold temperatures. So they're also operating at this minus 374 degrees Fahrenheit, which is the typical operating temperature of the system. But for the NIRCam, Lockheed Martin was actually the prime contractor, and they selected I-220H as the optical bench for that system. And it's very interesting because on one hand, we have a O30H material for a lot of the beryllium on the James Webb, and here we use I-220H material. And why was that? Well, you know, the I-220H is a stronger material, and it has a much higher precision elastic limit or micro yield, and optical people just like that property. The downside of I-220H is it's more difficult to manufacture and machine. So I don't think we could have ever used I-220H for the mirrors because they were so large, but it was a perfect material for this optical bench, and it's an extremely accurate piece of equipment. You know, the telescope is looking back 13 billion years. It's at light signals that are coming from the start of the universe. And to be able to detect and focus and differentiate all of that information takes incredible accuracy. So NIRCam was really a very interesting instrument. The other 3 instruments, it's all about having different missions. You know, there's a mid-range infrared camera, and there's spectrographs, and there's other things going on there as well.
That's exciting. It's good to see that there are more than one applications of beryllium on this telescope that's about to go up. So as we're closing up, what are your thoughts about seeing the telescope getting ready to launch? As you said, this program started in 1996, and it's finally getting ready to go into space.
Well, from my standpoint, this has been an exciting program for the last 25 years. We've been patiently waiting for launch for several years now. It's going to be exciting. This is truly, the Webb telescope will truly be a national treasure. It's been certainly very expensive telescope to launch, but the fact that it will do things that no other telescopes will be able to do. It's going to sit 1 million miles out from Earth and look back to Martin at the beginning of time, look back, billions of years ago to the start of for the initial light of looking for traces of light from the Big Bang. For us at Materion and at the factory where we did all the work or much of the work, this was a once in a lifetime opportunity to be part of something that people will be talking about for years and years to come. So it's an exciting time for us. I expect to have a bit of a celebration when it launches in October. We're certainly looking forward to it, and even more so several months later when it's opened up in its position and the first light comes and they'll see things that people have never seen before. This is just really exciting things to happen. And astronomy will never be the same after this.
How do I follow that, Keith? Yeah, I mean, for me, it's a huge milestone to see this program actually launch. But it is a milestone. It's a very important milestone. But the incredible journey that Space Telescope is setting upon is just starting. As Keith said, it's going to travel almost 1 million miles from Earth to the L2 Lagrange point. It then has to unfurl this incredible complex mirror, and it has to focus from what Keith said, those actuators. The whole mirror system takes several months to actually focus and get tested. And then I think the real big thing is, hey, the first pictures, the first images that scientists are going to get back, and what do we learn about the universe. And the mission is involved, because as Keith said, it was to understand how the universe formed, but it's evolved into now we can understand the chemistry and the atmospheres of many other planets that may be able to support life. So that's really interesting. But I think it'll be a good time to reflect on all the people I've worked with in the beryllium industry over the last 20 plus years, and certainly the people that were involved with James Webb, from everybody that was involved in that program. You have to feel good about being part of something, as Keith says, that's significant. Great job by the Materion team, for sure. Thank you.
Yeah, it's definitely exciting to get to be a part of history, and I'm excited to see those first images when they come. So I just want to thank you guys both, Keith and Martin, for sharing your stories. And working on the James Webb Telescope has certainly been a point of pride for the entire Materion team. And it's great to hear your passion and all the involvement you had in making this successful over the past 20 plus years. As listeners, I hope you enjoyed learning more about Materion and our materials that impact our today, tomorrow, and beyond. And as we wrap up today's episode, I, with the rest of the world, will wait with anticipation and excitement for the James Webb Telescope's launch date. Thank you for your time today. And until next time, explore, inspire, deliver, repeat. Goodbye.
Thank you for tuning in to this episode. Be sure to follow Materion on our social media channels, as well as visit our website for more information about our innovative material solution.